I want to talk about the QSPI Max 2 I built. Basically, I wanted to do remote development of firmware, but still have a system at my office where I can just test images. And it also would be quite useful to be able to automate the testing of images on real hardware to see if there was some regression or if basically if change broke something. But I don't I wanted to have it in a way that neither the firmware image nor the board design needs to be changed for that. And also, basically that I can just set it up once, put it in some space, and just have it running there. And also for systems like the newer atom-based, they use a 1.8 volt flash and not the usual 3.3 volt. So that should also be supported. So what some people do is just plug a test clip on the target board, connect it to programmer. Yeah, but that might even damage the system because often the flash is directly connected to the same voltage rail as part of the chipset. So when you connect just a clip to the flash and power the flash chip via this clip, you also power up some part of the board, and that usually violates the power sequencing requirements of the chipset. Sure, on some boards there's a diode in the voltage supply line for the flash. There it's not a problem, but it's usually in mass-produced designs they just leave out this diode and just put a 0 ohm resistor there because it's half a cent cheaper. Also the data lines from the programmer and the target system might interfere. So it's, I mean, it works when you just want, or it often works when you just want to flash a board once, but for development you can't really use that. So what a lot of people use is the EM100 flash emulator. It's, I think, $400, $500 around. But for hobbyists, it's rather expensive, and also when you want to test large amounts of systems, for example, like 30 systems or so, you want to see if some change breaks the firmware for those systems. That gets expensive really fast. And also the old version you can get for a bit cheaper in used. That I think it only works for up to 20 or 25 megahertz. So you need to make some changes to your firmware so that the SPI controller doesn't switch to like 50 megahertz mode. There's also a new system, the SPI by Tremel Hudson. I think it's still a bit in development. It's basically based on a IS-40 FPGA and some SDRAM. But it also has limited maximum frequency because the problem there is the latency. Basically, the protocol from the flash chip, you send the flash chip an address, and after that, after a fixed amount of time, I think it's one byte without data, you have to send the data. And when you store the data in some DDRM or so, latency becomes a problem there. Basically, you don't get the data fast enough from the RAM to send it to the host when emulating an SPI flash. That's I mean, I first tried to build my own SPI flash emulator, and that wasn't that easy. So another approach would be the spiculator. Basically, there you also use a clip to connect to the flash, but with the spiculator you can you can basically isolate the programmer from the system. So at least when the system runs, the programmer doesn't interfere with the system anymore. But yeah, when programming, that still might be an issue. Yeah, so I more or less based on that, I created the QSPI Max 2. Or yeah, it's first the QSPI Max and then the second revision. Basically, I put yeah, that's the thing in the. Do we have a laser pointer? No, but basically this is the QSPI Max 2. On the main board, I removed the flash and put some small interposer board there instead. Then I put the flash on a small PCB and connect that all together with the QSPI Max 2 in between, and connect the programmer there. Yeah, that thing uses a real flash chip, so that's 100% compatible with the protocol, and yeah, also if the flash, yeah, it supports all commands the flash chip support. And yeah, the nice thing about that is that the programmer can select if the flash chip gets directly connected to the main board. So you can, I think I tried up to 50 or 60 megahertz, and also a quad SPI that just worked. And you, and the programmer can say that the flash chip should be connected to the programmer. So basically, you can put the system in reset, connect the flash chip to the programmer, rewrite the contents of the flash chip, then connect the flash chip back to the main board. It's just toggling one GPIO pin at the programmer, and then release the board from reset, and you can execute the newly flashed firmware image and see if it boots or not. Hopefully it boots. Yeah, and it's designed to be compatible with both 3.3 and 1.8 volt flashes. The programmer, however, needs also to be able to support the different voltage, because the multiplexer directly connects the data lanes to either the board or the programmer. So yeah, the voltage level must be compatible. And it uses two ideal diodes. There are those two things. Basically, it's a P-channel MOSFET and an op-amp. So when only the board is powered, the flash and the multiplexer get the power from the board. And when the board is powered off, but the programmer wants to power the flash, the multiplexer and the flash gets powered from the programmer, but the current can't flow back into the board. So that's you can't accidentally inject some current in the voltage rails on the main board. So you can't cause damage to the main board there. Yeah, and lessons learned from the project: try to avoid unneeded complexity, because yeah, it's for that use case just a simple or just 6 multiplexers, 2-to-1 multiplexers are more or less sufficient. Then it's really important to optimize the hardware design for manufacturability. Like you see here, that board has only components on one side. The first revision, the QSPI Max without the 2, had the header to the main board on the bottom side, and the header for the flash and the programmer on the top side. And yeah, basically that was really hard to manufacture, because when you put that through a pick and place machine and a soldering machine, you can't really glue the parts on the bottom side to the board, because they don't have that much area where you could put the glue there. And so yeah, they're relatively heavy compared to the area where the connector is soldered on the board. So basically, the problem is when you put it through the soldering process the second time, the parts on the bottom side are very likely to fall off. So yeah, I had to do that redesign with just with components on just one layer. Yeah, and it's also quite useful to talk to your field application engineers from the companies making the parts, because I'm using some really nice 90-degree angled connector there, but it's half pitch, or 0.05 inch pitch. That was not that easy to get. Basically, there's one manufacturer making those. And also the connection to the programmer, I wanted to use some other connector there, basically this style of connector with a ribbon cable, but those ribbon cables are really expensive and sort of flimsy. But yeah, so I went to the flat flex connector that costs, I think, a third, or with the connectors in the cable, and also does the job. So yeah, the project is open source. It's currently not available to be bought, but I want it to be. So yeah, I'm still need to work on that. And yeah, do you have any questions?
Please queue up at the mics. Okay, at least take the mic. Oh, sorry.
I have a question. You said you had to put the board under reset while programming the flash. Does that require any additional wire that we didn't see on the photograph, or is there a reset wire on the flash chip that goes back to the main CPU? Or did I misunderstand something?
No. You also need to connect the reset of the main board. But the board doesn't have to be in reset for the flash to be programmed. But when you connect the flash to the programmer, you disconnect it from the main board, and that also might cause some weird stuff happening.
I'm just wondering if you put the board on the reset with a separate wire. Couldn't you almost program it with a clip on? Because on the reset, I would assume that the main CPU goes high C on the SPI wire, so that your clip would not interfere with the main CPU, and the flash would be powered from the main power supply on the board.
Not all processors or system on chip put the connection to the SPI flash in high resistance mode when they're under reset.
Okay.
Had that issue, I think, with the network card.
Okay, makes sense.
Hi, Felix. Just a quick question on the pricing for the BOM. How much it would cost to build yourself? Parts cost.
Part costs are, I think, between $10 and $15 for the whole set. But the PCBs, basically here it's it's not that well to see here. Basically, you need some special process where there's copper at the edges of the board. I have a few samples with me, so you can have a look at it later. That has some initial setup cost, basically once for the whole set of boards. And the board itself, it's also a four-layer board, so it gets cheap when you order like 100 or 1,000 from it, but just for 10, it's a bit more expensive.
And another quick question. Because it's a MUX, we couldn't use it to monitor the SPI bus at the same time?
Didn't get the question?
So is it because it's a MUX, we couldn't use it to monitor the traffic on the SPI bus at the same time?
To monitor what's on the SPI bus? No, basically only the flash can be connected to either the board or the programmer, but the programmer can't sniff what's on the bus. But yeah, for this solution, it's just one chip that's readily available. So yeah, went that route.
All right, I guess that's it. Thank you very much.
Yeah, thank you.